So, looking at question number 3. For this problem, we're going to assume that you have a class roster with 2 corresponding 1D arrays. A string array containing the list of names and a corresponding array of integers containing the list of UTEP IDs. So the first thing I like to do on a problem like this is to draw myself a little picture, right? So we have a list of names, Carlos, Daniela. These names should be familiar to all of you by now. Alex, Isaac. And we each have an ID. So let's say I'm 9, and Carlos is 7, and 4, and 12, and 7. No, 8. Sure. Okay. So now we have this set up to our problem. Notice that one of those arrays is integers, one is strings, so we can't just put them in a 2D array, right? We have to store them separately. So what we're asked to do is given, right, so assume that for any given index, the name corresponds to the ID, right? So my ID is 9, Carlos's ID is 7, and so on. So the first scenario says, if the two arrays are sorted by UTEP ID, what's the largest number of computations needed to find a student's name given their ID? So let's go ahead and sort these by ID, right? The smallest one is 4, and then 7, 8, 9, and 12. That means that this is also sorted, right? 4 is Daniela. 7 is still Carlos. 8 is Alex. Nope, is Isaac. I'm 9. And Alex is ID 12. Okay, so notice that it changed the sorting of the names. They're not in order at all. They weren't in order before either. So what's the largest number of computations we need? So we're given their ID. So we're given a value inside this sorted list. And we want to search through that sorted list. Well, we know if it's a sorted list, what methods can we use to search through it? Well, for a sorted list, the fastest way to search through it, right, is using binary search. Right? Because we're searching for an element in a sorted list. So we know we can use binary search, and what's the largest number of computations that we would need to do that? Well, in this case, it would be log of 5, but in most cases, it's log of n, right? Using binary search. That's the worst case running time of searching for an element in a sorted list, right? And because we're looking for the ID and it's sorted by ID, we can use binary search. So what's the best case scenario for using binary search? Again, here, sorted by UTEP ID, we're given the student's ID. Well, we would still use binary search, but here the best case is order 1. Right? If that first element, right, we happen to be given 8, that middle element is 8, we can return Isaac's name. Right? Okay, now, what about the case where it's sorted by, not by ID, but by name? So Carlos, and, nope, even I already messed up. Alex comes first, then Carlos, then me, Isaac. And in this case, Alex is 12, Carlos is 7. He ends up in the same spot again. 9. Daniela is 4. Isaac is 8. Right. So in this case, it's sorted by the student names, but we're given their ID, right? So it's the same scenario. We're still given their student ID, but instead of it being sorted by ID, it's sorted by something else. So in this situation, can we use binary search? No, we can't use binary search. So what's the other search algorithm that we know? Using linear search, right? And if it's linear search, given the name, what's the largest number of computations we might need to find someone in that list, right? Well, it's order n. So some of you wrote quite long answers for this question. And yeah, these aren't quite long enough, right? Because I say explain the algorithm, but we explained it in words. But this is about all you needed for this answer, right? Here, we can't use binary search because it's sorted on the thing we're not given. We could use binary search if we're given the student's name, but we're not given the student's name, we're given the ID. Okay, see you on question 4.